Okay, so welcome back. In the last class, we have discussed about the finite volume formulation of a given governing equation, and here we will start with a representative problem and we will try to solve by employing finite volume technique. So, here so consider this problem which is of source free heat conduction in an insulated rod whose ends are maintained at constant temperatures of 100 at the left face and at 500 degree centigrade at the right face, as shown below in this here you can see. So, this is the geometry which is shown over here, and so the one dimensional problem which is shown here. So, the governing equation is a typical heat conduction equation. So, that is ddx of k dt dx is equal to 0. So, we need to calculate the steady state temperature distribution in the rod, temperature at different points, and where thermal conductivity K equals to 1000 watt per meter Kelvin, and the cross sectional area of the rod is 10 into 10 to the power minus 3 meter square. So, how do we solve it using finite volume method? So, basically the first step will be to discretize it in a set of nodes. So, set of control volumes. So, how we can do that? So, if we try to discretize it in the form of equidistant control volumes. So, then so here say for example, this is the point 1, this is point 2, point 3, point 4 and point 5. Okay. So, this is basically discretized with the help of this 5 control volumes. So, now we will see how we can identify the temperature values at these chosen grid points, that is 1, 2, 3, 4 and 5. So, so this is the you can see the discretized domain over here. So, here so like we have started off with this equation, that is the governing equation, that is ddx of k dt dx is equal to 0. So, in this case we can see that there is no source term over here. So, that is why it is it simplifies. So, here in case of at least in case of point 2, 3, 4 which are lying at the middle of the domain the rod, there is no source term involved. So, here if we need to derive the finite volume set of equations approximated algebraic equations from this governing equation. So, basically we, like I discussed in the last class, we need to basically integrate it, we need to have a volume integral, and then from there on we can basically write it as from the east face and the way so like K E A E by delta x E and that temperature that is T P and T so here you can write as the T E minus T P. So, minus you have to write K W A W and by delta x here it will be P E and here it will be P W by so here T P minus T W. So, from here if you rearrange the terms and then simplify that governing equation, from there you will arrive at this expression, that is K E by sigma x P E plus K W by sigma x W P A W T P. So, here you have seen in the last class we have explained in the form of a property phi. So, that property here is the temperature. So, here we have mentioned in the form of temperature. So, here phi p becomes T p, phi e becomes T e and phi w becomes T w. So, here basically this term shows the this A p and this, and similarly the other, this one becomes A w the coefficient, and this one becomes A e the coefficient. So, accordingly this equation reduces as APTP is equal to AWTW plus AETE. So, so and here, because we know that thermal conductivity KE, location E, location east face, west face of the control volume. So, this is the typical control volume. So, here basically this is the east face and this is the west face of the control volume. So, here the value of Ke is equal to Kw is equal to K. So, because thermal conductivity which is constant throughout the that circular rod, and here the node spacing is delta x between two grid points, but only the difference is that the the distance between the boundary of the that is the left boundary and the right boundary and the nearest node, that is from left boundary it is node 1 and from right boundary it is node 5. So, that distance is delta x by 2. So, that is the half of the usual distance between two nodes in any other nodes which are interior to the domain. So, then the equation reduces to APTP is equal to AWTW plus AETE for node 2, 3 and 4. We will talk about the boundary nodes the formulation little bit later, and then so then accordingly we can identify the value based on this equation. So, you can understand from here. So, this is AW as I already marked. So, here you have to place the value of AW, that is K by Ka by delta x. So, you can see Ka by delta x. As I already mentioned that Kw is equal to K and delta x Wp, delta x Pe all are equal to equal to delta x. So, K by delta x into A is AE and then AW again is basically the K by delta x into A. So, as we know from you can also identify from here. So, basically what is AP? AP is nothing but the summation of AW and AE. So, that is what is written over here, AP is equal to AW plus AE. So, now we come to the treatment of the boundary nodes, that is 1 and 5. So, therefore, they require special attention. So, here there is a that difference is there, the difference like I explained earlier, that is you have to here it should be like the east face of the boundary. So, like if you are considering for point 1, then east east node from point 1 is basically node 2. So, that is here designated as TE minus TP. TP is the point of node of interest over here. That means, in case of point to node 1 it is T1 divided by delta x minus Ka, that is TP. TP means the node 1, that is east to the boundary is at TA. So, T1 minus TA divided by delta x by 2, that is the distance shown over here between the boundary and the node 1. So, where from we are getting this abbreviation? We are basically getting this from the same governing equation that I have written in this slide, and then if you just do the put those values, approximate and then rearrange the terms, you will arrive at this expression which is equal to 0. And so, this expression shows that the flux through control volume boundary A has been approximated by using a linear relationship between temperatures at boundary point A and node P, and in this case node P is node 1. Okay. So, we can arrange above as follows. So, that is K. So, we are basically rearranging this equation to arrive at this equation. So, here K by delta x A plus 2K by delta x A into Tp. So, is equal to K by delta x A into Te and plus 2K by delta x A into Ta. So, here we are not getting any terms with Tw. So, but our usual form is what? Our usual form is AP Tp is equal to AW plus AW Tw plus AE Te and plus SU whenever there is a generation. So, here in this case the nodal boundaries point nodes which are situated close to the boundary, we treat that boundary temperature as the source term. So, fixed temperature boundary condition is treated as a source term. So, that is why here we can, I mean, we have to go back to the original form of the discretization of the governing equation, like we have discussed in the last class. So, here we can see, because there is no term associated with T w. So, we can write that expression from rearranging this expression as this, where we can choose the value of A w as 0, and 0 multiplied by T w is nothing but 0. So, here from we can identify the individual values for the these coefficients, that is A w, A e, A p, as well as we can identify the value of S u. So, because we have to treat this case of fixed temperature boundary condition near node 1 as the source term, that is SU plus SPTP. So, here from this equation we can identify that SU. So, you just look at here. So, we can identify SU is equal to 2 K A by delta x into T A. So, I mean, as we know already that I mean that source term is equal to SU plus SPTP. We will understand how we can calculate SP in the next slide. So, this is we can understood how we calculate AW, AP, AE and SU from here, and then you can see. So, for node 1 AW is equal to 0, AE is equal to KA by delta x, and AP is equal to AW plus AE minus SP. So, here we have learned how we calculate the value of SU from seeing this equation from here, and so here we also put the value of SU. And then for I mean so basically, because I mean SU plus SV T I mean TP, so SU plus SP TP is equal to 0. So, from here you can quite easily identify the I mean value from SP, that is minus 2 Ka by delta x. So, then the control volume, the same treatment we have to follow for the I mean node 5, which is kept over towards the I mean right side boundary of the rod. So, which is situated at a temperature Tb. So, by doing the same treatment over here, we can identify the value I mean this expression. Again we have to equate the value of AW as 0, so that we can I mean estimate it, and so this is basically corresponding to the AP, and this is corresponding to AE, and this is corresponding to I mean this is corresponding to SU. So, I mean so here if you put these values in this table, so I mean you are getting AW as I mean at node boundary 5 I mean we are getting the value of AW as 0, and yeah. So, here in this case, because it is the I mean boundary is situated toward the east face of the I mean point 5. So, you can see over here this is situated at the east face and not at the west, like in the previous case in case of I mean node 1. So, that is why here there is a difference. So, here we will get the value of AE as 0, and so there is a I mean mistake in this expression. So, here the value of AE will be 0 and AW is Ka by delta x. So, AP becomes AW plus AE minus SP. So, and then SU and SP becomes minus 2 Ka by delta x and 2 Ka by delta x Tb. So, from here we can identify the I mean resulting set of algebraic equations corresponding to each individual node. How we can get that? So, you can see that we have already written this expression for I mean. So, this expression you need to repeat, that is I mean APTP plus is equal to AWTW plus AETE plus SU. So, if you just put the values of AP, AW, AE and SU identified at each of the nodes of this rod that we have discretized before, I mean so 1, 2, 3, 4 and 5. So, then if you put the values of respective I mean AP, AW, AE, and also because we already know that Ka by delta x, how do we determine Ka by delta x? K is nothing but thermal conductivity that we have initially mentioned, that K equals 1000 watt per meter Kelvin. So, so it is 1000 watt per meter Kelvin into the area is basically the 10 into 10 to the power minus 3 meter square. So, 10 by 1000 and then delta x. So, what is the value of delta delta x, because here it is a one dimensional rod and here delta x value is the total value is 0.5 meter. So, that means it is divided into 5 equal intervals. So, it is nothing but 0.1. So, you can so 1 by 10. So, it is becoming 1000 into 10. So, the value of K by delta x becomes 100. So, that means the value of AW becomes 100. Okay. So, then the value of this. So, this is the value of AW first equation. You can see that based on this matrix which is written for all 5 nodes, where in case of first node AW is 0 and then AE is 100, SU is 200 TA, SP is minus 200, and this is the value of the AP for AW plus AE minus SP that we have discussed before. So, likewise we can get the value of, so for the first node AP is 300. So, you can put that 300 T1 is equal to so that is TW. So, from the first node the west side of the node is basically the boundary. So, that means that is 0. So, then AW TW it is basically 0 and then AE. So, then it is equal to AE. What is AE? What the value of AE is also for the first case is Ka by delta x. So, that means it is 100. So, that means it is 100 into T2, that is east to the first point, east to the first node is node 2. So, that is that is why we have written over here AETE, that is 100 T2 plus so SU that is 200 TA, that is over here you can see 200 TA. So, this is how we can get the approximated algebraic equation for the first case first node. That is we can arrive at this expression. Accordingly, we can get the algebraic equation for each individual node, and then if we just arrange it in the form of this matrix. So, you can see. So, this is basically a so in this matrix there are 5 rows and 5 columns. So, it is a 5 cross 5 matrix into it is a column matrix where there are 5 rows and only 1 column is equal to 200 TA. It is again another column matrix. So, we can get by doing a simple MATLAB calculation, or we can also do by Gauss elimination method. We can arrive at the values of the temperatures at individual nodes of this rod. So, this is how you can calculate the temperature distribution in the 1D rod. So, this is how we can get the estimate the values at each nodal point of this rod T1, T2, T3, T4 and T5. So, the values are written over here. So, this is a typical example of how we can apply the finite volume discretization technique to solve the problem, and so it can also be applied to several complicated grids. So, this was the example of a heat transfer problem, but it can also be applied to fluid flow problems with relative efficiency, and we can achieve results which are near accurate. And so that is why finite volume is very much popular for solving fluid flow and heat and mass transfer problems. So, now we will move to the finite element method. So, in case of finite element method shares many similarities with the finite volume method. So, in the FE method the domain is divided into discrete volumes or finite elements that are typically unstructured in 2D. And so, here the key difference with finite element and finite volume is that in case of finite element, the equations are multiplied by a weight function before being integrated over the entire domain. So, in the simplest form of finite element, the solution within each element is approximated by a linear shape function, ensuring that the solution remains continuous across element boundaries. So, this shape function is typically constructed using the values at the element corners. So, I mean here the solution is basically achieved by minimizing the error, minimizing the residual. So, which is achieved by setting the derivative of the integral with respect to each nodal value to 0. So, this process leads to a set of non-linear algebraic equations that we subsequently solve by matrix algebra, and then we basically achieve the value of the particular primary and secondary variables at each nodal points within the finite element, and also thereby within the entire domain we can achieve the distribution of these primary and secondary variables of interest, that for which we are basically solving the set of finite element equations. So, one major advantage of the finite element technique is its ability to handle arbitrary geometries. So, there is a vast body of literature on constructing grids for finite element. So, but the one thing I would like to highlight over here, that in case of finite solid mechanics problems, we generally go for finite element techniques, because it can be very efficient with unstructured grids also. So, in case of and also another thing is that in most of the solid mechanics deformation problems are basically the elements also gets deformed with the body. When it undergoes deformation, it undergoes shape change. So, the domain does not remain fixed, domain also evolves with the applied load or the deformation conditions. So, it is easier in case of finite element to subdivide the elements into which is also called remeshing. So, that is why we often use finite element technique for solid mechanics problem, which is not the case in case of fluid flow heat transfer problems, where the domain relatively remains fixed and the flow goes within the flows past the domain. So, this is a major difference. That is why FE is popular with solid problems. Of course, there are many applications of finite element method in case of fluid flow problems as well, but it is primarily applied to solid mechanics because of the benefits explained to you just before this. And so, these are the typical examples. So, you can see over here again it is shown to you before. So, this is a classical welding heat transfer and whirlpool formation problem, which is solved using finite element method, and this is another problem which is showing the example of a rolling deformation to a plate, which is solved using finite element method. So, so now we will discuss the key considerations in FEA of metal. So, the number one is nonlinearity. So, the geometric nonlinearity. So, this arises when deformations are large enough that the initial geometry changes significantly during the analysis, requiring updates to the stiffness matrix. So, material nonlinearity, this involves changes in material behavior such as yielding or strain hardening, which must be captured accurately for realistic results. And then there is contact nonlinearity. So, there are three kinds of nonlinearity: geometric, material, as well as contact. So, what are the contact nonlinearity? So, there are two or more bodies interact when so there can be friction, there can be separation, there can be sliding of one body past another body. So, this is the reason for the nonlinearity, for which nonlinearity arises in case of contact problems. And then there is a temperature effect. So, thermomechanical coupling. So, in many applications like like hot forging, hot rolling, there are several examples of that, where we see the the metal piece or the composites, whatever, they undergo deformation at a combined thermomechanical loading condition. So, the FEA must account for the interaction between temperature changes as well as the mechanical behavior, that is thermal expansion leading to additional stresses, and then creep and thermomechanical fatigue. So, when a typical solid is subjected to I mean high temperatures, and then they can slowly deform even under their own weight, and which is often termed as creep. And also because of the thermal cycling, the specimen undergoes, it can cause fatigue to the specimen, where the metal eventually fails after a certain number of cycles. So, these are the some of the considerations. Some other considerations are time dependent behavior, like creep analysis is significant in metals subjected to high temperatures and sustained loads. FEA can model creep by incorporating time dependent material properties, and then it can also be useful for fatigue analysis, where we can basically predict the fatigue life of a metal component which is under service under and experiencing cyclic loading. So, we can predict SN curves, that is stress versus number of cycles, which are used to determine how many cycles a component can endure, it can withstand before the final failure. And then validation, so comparison with experimental data. So, of course, as I told you before also, that these numerical methods are useful, their results are useful only when they are validated against the critically performed experiments. So, that validation is essential to qualify the data to be implemented for prediction of real world processes and problems. So, that there are applications of finite element method which is manifold. It is applied to almost all the industries like automotive, aerospace, manufacturing, electronics, defense, and so on and so forth. And so, the challenges of and future directions of FEA, the computational resources. So, with the increasing complexity of the processes and the products. So, here we specifically talking about process modeling. So, there is process innovation being happening in the domain of manufacturing in every day. And after the invention of additive manufacturing, it becomes even several groups worldwide working on several processes, and they are trying to push the boundaries of the knowledge. And then so these innovations can be make the developing the accurate process models challenging day by day, and that is why we need more number of grid points, we need more nodes, which in turn makes the simulation even more challenging, and that is why the role of high performance computing comes into play. But however, there is a solution proposed to the to reduce the computational cost is reduced order modeling. So, it is useful to overcome computational limitations. So, ROM techniques are being developed. So, these methods reduce the complexity of FEA models while preserving essential behaviors, allowing faster simulations. And then there is the integration with AI. So, the newer concepts of machine learning, it also speaks of getting trained based on the simulation data, and also to work in conjunction with this physics based models like finite element method. So, where it can also lead to the prediction of some of the parameters, where some of the parameters are getting evaluated by FEA, and they can work in conjunction with this AI and machine learning based models to integrate the efficiency of prediction, as much faster and accurate predictions, and it can be applicable to various domains, like it starting from the complex material behavior like plasticity, fracture, fatigue, creep. It can also be applied to optimize the several manufacturing processes like several casting, forging, and welding processes, along with the optimization of design and design of products, and also their assembly cycle. And so, the newest and the most effective concern in the process modeling domain is the advent of multi-scale modeling. So, what it speaks of? It speaks of coupling the several length scales into one. So, that means a model, macro model, which will be capable of feeding the microscopic informations into it, and it can predict the phenomena which is starting from macro, it can go to the micro. For example, like we have discussed earlier also about the problem of casting solidification, where we can we can develop such a model which can simultaneously predict the temperature distribution, velocity, viscosity distribution within the solidifying melt, and also it can, the same model can predict microstructural informations like dendrite, I mean primary and secondary dendrite arm size, and also I mean how the different phases are distributed, what is the volume fraction of individual phases, what will be the morphology of the individual microstructural phases. So, if we can club this both macroscopic and micro and even mesoscopic information at one place, then we call it as a truly multi-scale model. So, that is the need ahead. And then, so if we now start with the finite element. So, finite element method deals with the simplification of the complicated partial differential equations into a set of finite element equations. So, basically we now we will try to revisit the understand how we can derive the develop the stiffness matrix out of this governing equation, which is shown over here. So, it is that is written over here. So, dd minus ddx into a du dx plus cu minus q is equal to 0 between when x varies between 0 to L. So, what are the boundary conditions? Boundary conditions. So, u here u is the primary variable. So, u at 0 x is equal to 0 is u 0 and a du dx at x is equal to L is q 0. So, here where a is equal to a x, c is equal to c x and q is equal to q x, u 0 and q 0 are the data, that is known quantities of the problem. Equation arises in connection with the analytical description of many physical processes. For example, conduction and convection heat transfer in a plane, wall or fin, flow through channels, pipes, transverse deflection of cables, axial deformation of bars and many other physical processes are described here. You can see the how we can. So, our goal is to achieve the formulation of stiffness matrix. So, the solution within a typical finite element, that is omega e, is of the form the primary variable u e can be expressed as summation of j is equal to 1 to n u j e psi j is the shape function x, where u j e are the values of the solution at the nodes of the finite element and psi j are the approximation functions over the element. The coefficients u j e are determined such that it satisfies in a weighted integral sense. So, as discussed in the necessary and sufficient number of algebraic relations among the u j e can be obtained by recasting the differential. Now, we basically what we will do, the differential equation. So, basically we have to get a weak formulation of this given differential equation, the partial differential equation, and which is also called the Galerkin method, and therefrom we can get the we can derive the stiffness matrix. So, how we will do it? So, basically we are integrating it over this finite element, that is omega e. And then, so we are also multiplying it by the weight function. So, then the weighted integral form becomes like this, delta E w multiplied by this differential equation dx, which is equated to 0. So, where w x denotes the weight function and omega e is the finite element in consideration, is the domain of a typical element. For u is equal to u e for and each independent choice of w, we obtain an independent algebraic equation relating to all u j e. So, similar like we have discussed in case of finite volume technique, in case of finite element also we will get a finite element equation for each of the nodes of the element under consideration and thereby for the entire domain, and we will get a finite element equation for to solve the value of the primary and secondary variable at each of the node points of the element. So, so a total of n independent equations are required to solve for n values of the primary variable u j e. How we will see? So, the first step is to multiply the governing equation, differential equation with a weight function w, like we have discussed already, and then basically we need to integrate over a typical element. So, the second step is to trade differentiation from u to w using integration by parts. So, as we all know about the integration by part formula. So, here it is basically in case here it is u dv dx dx. So, then we will get u v minus integration v du dx dx. So, this is what, so this formula is being applied over here, and therefrom we are getting this expression. So, I mean which and then we, if we rearrange the terms, then so I mean, so we can arrive at this expression, which is integration x a to x b w d dx a du dx v is equal to minus integration x a to x b w d dx a du dx dx plus x a to x b a dw dx du dx dx. So finally we arrive at this expression from here, and then this is the final form, and then I mean, so the third and last step is to identify the primary and secondary variables of the variational weak form. So here w a du dx x a to x b, as a rule the coefficient of the weight function in the boundary expression is called the secondary variable, and its specification constitutes the natural boundary condition. So here I mean a du dx is identified as q, that is the secondary variable, and u is the primary variable. So in writing the final form of the variational, that is weak statement, we assume that all boundary conditions at the element level are of the natural type. So they can be included in the variational statement, and we can write that I mean q a is equal to nothing but minus a du dx at x is equal to a x at x a, and q b is the I mean it is positive. So here I mean, so for example, if you are dealing with a I mean deformation problem, so then you can assume that one end of the bar, the I mean it is this sign, this negative sign is nothing but the I mean direction of the applied force. So in one end, if you are talking about application of force, the force is negative, which is because it shows the it is a compressive nature, and another end it is positive, which shows it is of tensile nature. This is just to for your understanding. So we will go ahead with the I mean formulation of the element matrices. So for additional details on heat transfer, so with the notation, the variational form becomes like this: 0 is equal to integration omega e a dw dx du dx plus cw u minus wq dx minus wxa qa minus wxb qb, that is what we discussed before. So this completes the 3-step procedure of constructing the weak form. So the weak form contains two type of expressions, those containing both w and u and those containing only w. So then when the when it is containing both w and u, it is in bilinear in nature, and when it contains only w, it is linear in nature. So we group the format type into a single expression called the bilinear form, and that is designated as bwu, which is equal to integration omega e a dw dx du dx. So this is because of its bilinear nature, and then cwu, and the linear terms are grouped together in another function. So we denote all terms containing only w. So L, so we are terming it as LW, the linear form. So integration omega e wq dx plus wxa qa. So because if we are taking these terms in this side, all these negative terms becomes positive, and from here we can arrive at this expression. So LW is equal to this. So the variational statement can now be expressed as BWU is equal to LW. So which is called the variational problem associated with so the finite element model based on the weak form transforms the differential equation into algebraic equations for nodal values uie and qie, incorporating natural and essential boundary conditions. So it allows flexible interpolation without pretending the approximation degree, supporting various levels of accuracy. So so we are stopping with this class, and in the next class we will discuss about how we are finally arriving at the element matrices, and how we can basically solve a given problem within the finite element framework. Thank you.